Alrighty, changing tack slightly. We are going to be talking about floods and flood frequency. This is a component of my PhD research that I'm doing at Massey. So I'm evaluating historical flood frequency and changes in erosion, because if we're going to model all of these things for our future, we kind of need to know what's going on or what has happened in the past. And as Cyclone Gabrielle really emphasised, in New Zealand we have an extremely poor understanding of our past flood history. We don't have a great understanding of our flood frequency, and we have a particularly poor understanding of our range of flood magnitude. So what those high magnitude floods are in our catchments, and what that means for all of our infrastructure and all of the sort of erosion mitigation that we're trying to do. So I'm using fluvial archives, so the records that we can obtain from within our river catchments themselves. So this means that I am really closely tied to the flooding environment and where that behaviour is actually happening, rather than being one step removed. And I'm also sort of doing this research in areas that are really proximal to the places that are going to be impacted by these big flood events when they happen. And to do this, we're using CT scanning, which is a relatively novel method for evaluating flood frequency in these sedimentary packages. So I'm doing this in the Whanganui, where I'm looking at Artine Bend, which is just in here, so down in the lower reaches of the catchment. This slide was made for an international audience, which is why it's got references to Lord of the Rings on there. But yeah, we're working in that bottom of the catchment, which means that we're capturing sort of all of that broader catchment behaviour. We're capturing those, not those sort of small sub-catchment floods, we're capturing those really, really big events that are impacting the entire river system. So this is building on previous research done by Ian and a couple of others. So they did this research in 2018 and developed a 2,000-year flood record from the same location. They did this using ITRAC's geochemical data. My intention was to do the same thing, but my geochemistry was slightly more complicated for reasons that I'll get into. And they hypothesized that the sort of initiation of my bend cutoff, so how my sort of record was created, was the Taupo eruption 1700 years ago. So 4 more cores were collected in 2020, and I have 3 of those on screen. We have 1 core from the entrance of the bend, so that's this one here, and it's 6 meters long, and within this core we have 3.5 meters worth of material that's directly attributed to that Taupo eruption. So that sort of shows the scale of material that was deposited into the catchment, and this has important implications for the information that I can get out of these remaining 2 records. We then have 2 12-metre long cores from around the bend. Our main focus is Artine 4, so that's this core, 12-metre core in the middle there. And then we also have Artine 1, which is from an alluvial fan further around the bend. For the rest of this presentation, we'll just be focusing on Artine 4 though. So this is our chronology. So right off the bat, we extended our record by 3,000 years. So from Artine Bend, we have a total of 5,000 years worth of flood frequency information, which is really important because, yeah, we've got that really massive event that's had this really significant impact on our catchment and catchment behaviour about halfway through. So this is the Taupo eruption deposit just in here. And how this stacks up in terms of timing, this period here is all pre-eruption material, and we have really different sedimentation through this period. We've got alternating sections of peat accumulation, where we've got stable sort of low frequencies of these really big floods that's interrupted by these flood deposits coming through that bend cutoff. We have our eruption deposit right in the middle, and this provides a really useful isochron for sort of refining our age model. We have, these are slightly different colours, but they're not really showing up on the screen, but that's all right. We have a post-eruption phase, And then moving into the top section of the core, we have a period that sort of cover Māori arrival into the catchment and into New Zealand, and then the top section of the core. So a really, really small amount of the core is actually contemporary and that sort of modern flood record. So, like I said earlier, we used CT analysis to sort of start building out this preliminary flood record. This is very early doors on this, but CT provides information on core composition and density. It uses X-rays to get that density information, and we end up with images that look like this, where we have these really sort of sharp contrasts that we can pull out density data like we see on these two other images. Our density is related to the composition of our core, and particularly in R1084 we have really strong contrast in density, and that we've got these peat deposits which are really light, really airy, full of organics and full of air, so they're really low density. And then we have these flood deposits coming in over top that are almost entirely lithogenic and comparatively really, really deep. So I can use a really simple method to classify my density data and start extracting out my flood events. So that's what we can see on screen here. So to do this, I identified what the sort of average density of a peat deposit was to work out a threshold. Everything below that threshold was classified as peat. Everything above that threshold was classified as not peat. And can be identified as a flood event. So everything in orange is those peat deposits, and it's this really, really dense stuff here that are our flood deposits. And we can see these big spikes here correlate with where we can see these events in our record. So what we end up with when we combine this with our chronological information is we get a sort of estimation of our flood frequency throughout the 5,000 year period. So that's what this schematic is here. So we have periods of time that are flood rich. So we've got a really, really high frequency of events, lots of events occurring really quickly. And then we have flood poor episodes where there's not really much going on or not much being recorded at this site. Within an episode, so whether it's flood rich or flood poor, there might be periods where there's sort of less flooding or more flooding and so on. And then we have these 7 particularly extreme events identified. So these were deposits that were particularly large within the core or had these really, really strong density signatures. So we pulled them out for further analysis. And those are the ones that are marked in yellow in this diagram. So we've got 5 different periods of increased flood frequency through this record, and these sort of roughly correspond with other records that we have for flood frequency around New Zealand. They're slightly out of step, but this makes sense. The sort of main record that we have for flood frequency in New Zealand is from the east coast near Hawke's Bay. And the other ones that we really have are down in the South Island. So we've got pretty different climate drivers between those two sites, and then different climate drivers or different expressions of those climate drivers again at the Whanganui, where we're sitting sort of in between those two different extreme records. So the fact that this record is out of step with the east coast of the North Island, which is strongly influenced by ENSO, and then slightly out of step again from the lower South Island, which is strongly influenced by the strength and position of the southwesterly wind belt, is kind of to be expected because we're sort of in the middle ground between the dominance of those two drivers. The other thing that's really important for us to sort of pull out of this record is event magnitude. So the events that we really, really care about are those events that are really, really extreme. Those are the ones that are going to be the most damaging, they move the most material, that kind of thing. And we actually have 2 very different records within R1084 because we have the Taupo eruption in the middle of the record modifying our channel connectivity. So prior to the Taupo event, we are capturing those really extreme events, but we're also capturing some of those sort of smaller, more moderate, not day to day, but maybe year to year sort of large floods. Whereas post that event, where we've got sort of 6 meters worth of material plugging each end of the bend, we've got a really significant reduction in that connectivity, and that means that the floods that we see post-Taupo are of a higher magnitude than we previously thought. So everything in that top section of the record, is more extreme than that was necessarily interpreted as when that pilot study was first done. So our sort of preliminary findings on this record is our bend is much older. We have this much longer record. We do have that really significant change in connectivity, which is influencing our record. And we've got about 5,000 years worth of flood information, which is really awesome for that future modelling that a lot of you want to do in terms of how our sediment's going to move through these catchments and how these catchments are going to respond to climate change. One of the things that I need to fix before I can move this through to publication is my chronology. So chronology, or our understanding of time, is sort of forms the backbone of these kinds of studies. The chronology that I have at the moment is really good. We have a lot of radiocarbon dates. We've got this really nice straightforward chronological diagram. But at the moment, even where we have event deposits, it's estimating a passage of time, whereas events like Taupo or any of these floods are instantaneous. So they're contributing to the accumulation of sedimentary material, but they're not contributing to the passage of time. At the moment, my model can't anticipate this, so I need to correct it. So instead of modelling time passing through this period, using the Taupo eruption as an example, I need it to model that this is one period of time and then continue on. So that's kind of what I'm working on at the moment over the next 4 weeks, hoping to get that done. Because I have sent away for additional radiocarbon dates, which are going to be filtered into this set of data. And I'm also hoping to have my density threshold refined. At the moment, it's probably overestimating how many floods are happening. So that needs to be fixed. And I need to do some verification of those particularly large events so that we can get an estimation of magnitude. And then we can funnel it all together into a publication by Christmas.